orbital forcing, in addition to increasing rain associated with the monsoon or decreasing it and leaving a signature in the river runoff, it also has impact on the surrounding seas. Remember, the monsoon is mainly the winds going from the ocean to land and land to ocean, and winds on the ocean we know already can generate currents, and these currents are always associated with Coriolis effect. So, what are the direct relation between monsoon winds and ocean response? So, we can look at the two examples. One is from the Indian monsoon and the other one from the African monsoon. So, here is the African monsoon region, which over orbital time scales has shown changes in the strength of the monsoon. So, as you can imagine, Sahara desert now and the Sahel region going from the lush green forests to thinner vegetation into desert has been greener before and has now is in a weaker monsoon and a desert situation. So, when these kind of changes happen, you can look at the winds that are causing the changes in the monsoon. So, that how is that affecting the ocean? That is the question. So, if you have weaker monsoon, let us make sure which is weak monsoon and which is strong monsoon. So, when you have a strong monsoonal circulation, you want to get winds from the ocean onto land. That is what brings you moisture, in which case remember that there are southeast trades on this side and northeast trades on that side, and within that you have this monsoonal circulation, and now you add Coriolis to it. So, if southeast trades are trying to push the water that way, Coriolis in the southern hemisphere moves things to the left of the direction of motion. So, water will be pushed away from the equator. On this side it will be slightly pushed towards the equator. So, south of the equator here you have what is called divergence. There is a separate module on upwelling and Ekman divergence. Ekman is the guy who first studied how ocean currents are formed by the forcing due to winds and how the Coriolis effect manifests itself in ocean currents. So, in his honor it is called Ekman divergence or upwelling. Upwelling means cold waters are coming up, and in the ocean it turns out that deeper colder waters have more nutrients like nitrate. So, when cold waters come up, the nutrients also come up, and if they come up near the surface where there is light, then the algae are going to be able to photosynthesize, because now there is light available and nutrients available. So, the strong monsoon signature in that case is associated with cooler sea surface temperatures over the ocean in response to a stronger monsoon, and a biological signature, which means that biology is going to leave some signature of a change in the strength of the monsoon in the sediments. Remember that biological production leads to sedimentation, and some of it like calcium carbonate shells and silica shells are preserved in the sediment. So, on the other hand, when you have a weak monsoon, then you have less of this Ekman divergence, the upwelling is reduced. So, you have warmer sea surface temperatures, reduced upwelling, reduced biological production. So, the change will appear in the sediments. In the same token, you can now imagine over the Indian Ocean, when the monsoon is coming in the summer months, the southeasterly monsoons, the winds are sweeping from the southwest over the Arabian Sea. Now, the upwelling is different. Across the equator, the upwelling happens because there is pushing of the water to the right by the Coriolis on the northern hemisphere, to the left in the southern hemisphere. So, you are pushing water away from the equator in both hemispheres. That means water has to come up from below to compensate for the water being moved away. Whereas, you are in one hemisphere, you have what is called along shore winds. So, if you try to drag the water along the shore like this, Coriolis in the northern hemisphere will push it to the right. You have winds along shore. These are called upwelling favorable winds. If the winds blow the other way, then they will be not upwelling favorable. Why is it upwelling favorable? Because as the water is dragged this way, Coriolis is pushing water away from the coast, which means again colder water has to come up. If the winds blow the other way during the northeast monsoon, for example, then the Coriolis will push the water into the coast, it will go down, so water will not be coming up, there will be downwelling instead of upwelling. So upwelling again brings cold waters, nutrients, so you have a strong signature of upwelling associated with the monsoon changes over India as well. So the main point is that the rainfall changes over land, that leaves river signatures on land as well as into the ocean, as we saw in the case of the Nile, and it also has ocean signatures where biological productions change. These are the things that help us to look at both hemispheres. For example, this is the signature in delta O18 from monsoon changes over Brazil, and this is the delta O18 signature from monsoon changes over China, the so-called broader Asian monsoon. We do not only have Indian monsoon, but there is also an Asian monsoon, as we saw in the map that showed the main monsoon regions. So you can clearly see that there is the orbital forcing in there. Insolation changes are shown by this magenta line, and the delta O18 signatures are shown by this green line, and you can see that they follow each other fairly well. Okay, so any change in insolation is resulting in a change in the monsoon strength, and that's producing delta O18 change by the same processes that we talked about before. Evaporation fractionates delta O18, and then during the rainfall you basically capture that signature in various things, like these are calcites from cave deposits, speleothems, as we said before, right? Speleothems, in case you forgot. My handwriting is not good, but you can look it up, and that is rainwater seeping into the ground and then dripping into the caves, and that fractionation that happens along the way is captured in terms of the monsoon changes associated with orbital forcing. And this has had historic records as well, and this is showing a cave from northern India, Sahiya cave, where speleothems were again collected and delta O18 signatures were measured for the past 6,000 years. So that's basically the so-called Holocene, where we have many historical evidences, archaeological and some oral translations into texts and so on. And you can see that this is the insolation change at 65 north. As we learned before, the insolation change at 65 north is critical because that determines the summer melting retreat or growth of glaciers, and then that leads to ice albedo feedbacks. So that has basically decreased going from 6,000 years to the present, with some variations along the way because of sunspots and so on. And the temperature record for the same period going from 6,000 to the present from the delta O18 signature in the Sahiya cave records the changes in the Indian monsoon, and it identifies all the periods where the rainfall had an impact on the civilizations that exist at the time. So HCO is the Holocene climatic optimum because the temperatures were kind of mild and they remained at that stage for a few centuries. And you had the mid-Holocene warm period, the Roman warm period, the Dark Ages appeared here as a cold period. This is the medieval climate anomaly here, during which time Greenland was warm. There was not enough glaciers, so agriculture was possible, and the Vikings had colonized Greenland. And then came the cooling associated with the Little Ice Age, which then refroze parts of Greenland, North America and Europe. It isn't clear whether this Little Ice Age was global or just happened over parts of Greenland and Europe. Nonetheless, that led to the extinction of Vikings, and we know that the Mohenjo-daro, Harappa and other civilizations, everything is kind of identified here. This is the Mergath culture, the early Harappan culture here, the mature Harappan and the late Harappan cultures are here. The early Vedic period is identified here along with late Vedic period, the Indo-Greek kingdom, the Maya Empire disappeared, and so on. There is the signatures of Little Ice Age and so on as well in historic records. So, monsoon changes and extended droughts have always played with civilizations. So, any region where the droughts persisted for multiple years because of the weakening of the monsoon always led to some perturbation in civilizations, and many have left records like the Mohenjo-daro Harappa civilization. So, this is the orbital forcing of the monsoon and its impact on the civilizations that existed at the time. See, the forcing of the monsoon is not just orbital, as we know that the tectonic uplift and the formation of the Himalayas has been a critical player in the evolution of the monsoon itself. When India was further south of the equator or in the northern hemisphere, but not yet crashing into the Asia and pushing into Asia to create these Himalayan mountains, there was not necessarily enough land close to the equator to heat it up and create this monsoonal circulation. So, the tectonic uplift has happened along with all these insolation forcing. So, you have basically created the insolation forcing to cross the threshold. Remember, early on we talked about the threshold of radiation for monsoon. So, you need the heating to be strong enough to create this land ocean contrast to drive winds and evaporation and moisture transport strong enough to generate this strong seasonal rainfall signature. Monsoon, again remembering what we said before, is Mausam, season. So, it's the seasonality is very important. So, the combination of tectonic uplift and orbital forcing together provided this crossing of the threshold on many occasions, which basically explains why there are episodes of strong monsoons and weak monsoons. Why is this important? Basically because with global warming we are producing also changes in radiation. How? For example, it turns out that the pollution and the dust that is related to global warming has actually reduced the sunlight over land over India. We will see later on in another lecture focused on monsoon that this reduced radiation and the reduced warming of land during the global warming period actually has reduced the ocean to land temperature gradient and actually has weakened the monsoon. And there is some evidence now that in the last 5 to 10 years the pollution has somewhat reduced. Maybe it's hard to believe, but overall it seems to be some evidence that the monsoon may be recovering. It had dropped by about 10% from about the beginning of 1900s to the beginning of the 21st century, but maybe now it's recovering. But nonetheless, these are the kind of feedbacks you want to emphasize in your course, where the forcing, whether it came from orbital changes in insolation received or because of human activities, the processes that act in terms of creating the temperature gradient, the land ocean heating, they are the same. They are radiative perturbations. Anything you do to change the radiative balance is going to affect the monsoon. So, this is why orbital forcing mechanisms are important to look at. The other important component of orbital forcing response in the climate system is of course the growth and decay of glaciers, the growth and retreat, advancing and retreating of glaciers. So, if you look at the surface temperature going from minus 30 degrees to plus 10 degrees, the main processes that determine whether the glacier grows, in which case it is accumulating mass, or it retreats or losing mass, ablates, depends on what are the rates of accumulation and what are the rates of ablation. Ablation is basically either winds blowing away the snow and reducing the growth of glacier, or direct radiative heating and melting of the glacier, or some interaction with the ocean at the end where the glacier flows into the ocean that begins to then accelerate the melting of the glacier as it is flowing down the mountain into the ocean, which happens a lot in Greenland and Antarctica, for example. So, those processes determine the net accumulation. So, as you can see, when it is very, very cold, there is accumulation, but as you begin to get closer to the melting point 0 degrees centigrade, ablation can increase, which is typically measured in meters of ice per year. Obviously, you have to be careful because the ice has a thickness, the glacier has a thickness, and it has an extent. So, you are typically measuring the extent, the how far it is extending back and forth. So, the ablation is typically the extent, but there are also ways to do mass budget, which is much harder. We won't get into the details here. So, here is the equilibrium line. Basically, when you subtract the ablation from accumulation, there is net ice sheet growth where there is more accumulation than ablation, obviously, and in the regions where ablation dominates accumulation, you have ice sheet melting. So, essentially you are looking for processes or orbital forcing or human activities or whatever, which is increasing ablation. Is there a way that human activity can increase accumulation? It's a tricky question, but you should think about it because it relates to how temperature affects humidity levels in the atmosphere. Global warming will make the air warmer, which will hold more moisture, which can technically increase snowfall. So, depending on the situation, there are parts of Antarctica, for example, where snowfall is actually increasing because the ocean nearby is warming and increasing the humidity, and there are other regions where the glacier is melting. So, the processes can be complicated. So, global warming doesn't necessarily always force the glacier to retreat. It can, in some special circumstances, increase the snowfall. So, we have to keep track of where it's increasing and where it's decreasing. So, we will see that there are very clear orbital signatures in glacier records, which obviously we use things like delta O18. So, when you change the tilt, again you have in the current condition the summer solstice is happening at the aphelion, so the farthest distance from the sun, and the winter solstice is happening in at the perihelion. Whereas, if you have switched the orbital parameters and you are having summer solstice happening at the perihelion and the winter solstice happening at the aphelion, then obviously you are going to increase the energy received in the northern hemisphere. Again, remembering that we are going to be interested in radiation at higher latitudes because, as we said before, typically we look at something like 65 north, which is a critical latitude for the reasons that where the Hadley cell ends, where the polar cell ends, and so on, where you can initiate the retreat of the glacier or the advancement of the glacier, and then the ice albedo feedbacks can kick in. So, this is according to the Milankovitch theory. We mentioned Milankovitch, who calculated the radiation changes associated with the orbital parameters of obliquity, precession, and the ellipticity, as we said. So, here are the examples of Milankovitch theory, which we already looked at, but we will put now in the context of insolation. So, if the summer insolation is on the upper side, anomaly is higher than some kind of a standard. So, let us say we are looking at anomalies with respect to the current levels of radiation. If the orbital change is such that there is more radiation than at present, that is going to drive net melting, and once melting starts, what happens? The albedo is reduced. So, more energy is absorbed, more glacier melts, and more energy is absorbed, and so on. So, you just need the orbital forcings to initiate the process, whereas if the orbital forcing is giving you less radiation than at present, then it can presumably start driving accumulation, and by the same token, when glaciers begin to accumulate, albedo goes up, more energy is lost to space, so it gets colder, even further growth of the glacier can happen, and so on. So, you have ice albedo feedback happening in both directions, and both are positive in the sense they begin to go in the same direction. Melting glacier will lead to more and more melting, growing glacier will give to rise to more and more growth of the glacier. Obviously, there are asymmetries, as we will see again and again, and I have mentioned it already several times. So, at the last glacial maximum, we were in an ice age, which means there was extensive glacial cover up to about last 20,000 years ago, it started melting, and there was a couple of hiccups, as we will see later on, but the so-called Cordilleran, Laurentide, Greenland, Barents and Scandinavian glaciers came pretty far down. As I mentioned before, it's all the way down to New York here, which left the terminal moraine, which has become an island called Long Island. There are records all over in Europe of the Scandinavian, into Eurasia of the other glaciers. Greenland glacier, there's plenty of evidence that it was much thicker, more extensive than at present. The additional thing we have to worry about for glacier response, which determines the complex timescales that we will see again, that we already looked at before, is that the heat capacity gives you time lag. So imagine that you have water being heated by a Bunsen burner, and the Bunsen burner is heating, you turn it off and then you start it on, and so on, just to give it a wavy heat input. And water temperature will start to warm, but with a delay because its heat capacity is high. And then when the Bunsen burner is turned off, water is still remaining warm, so it begins to cool with a delay, and so on. So you create this lag between the two waves. So if the wavy heating is provided, the wavy temperature of the water will be shifted. The same exact thing happens with glaciers. Solar radiation is changing as a wave, basically because we said obliquity is changing at 41,000 years. The ellipticity modulated precession is changing at 23,000 years, and so on. So if you consider the radiative forcing by the sun as a wave, the ice volume also has a wavy response, but it is shifted. And we will soon see that it might begin to merge the time scales, because if you started with 0 glacier and grew a glacier at 41,000 years of obliquity forcing, then when the obliquity forcing is removed, the glacier may not melt, depending on whether it's in a stage where the global temperatures are decreasing or increasing. Why do we say that? Remember that over the past 50 million years, we are in a cooling phase. Okay, so the glacier response depends not just on the forcing, but what is the background global temperature in which the glaciers are growing or melting. This gets a little bit complicated. So in a course, you don't need to worry about the very details of these kind of processes, but you just need to emphasize the phase lags that are involved and how they might produce timescales that are different than the forcing timescales, because the records collected about past glacial variability produces multiple timescales that are not always directly corresponding to the forcing associated with the orbital changes. Okay. So the time lag of 10,000 years is shown here for orbital forcing of 41,000 years, and for the precession forcing of 23,000 years, typically the time lag associated is something like 6,000 years. So you can see that the complications begin to build when you have precession and obliquity acting together. There is additional complexity because the glacier gets so heavy. So it literally begins to deform the bedrock that is under it. Okay? Remember that you have the continental crust, and then below that you have the lithosphere, and below that you have the asthenosphere. Asthenosphere is plastic, it can deform. The lithosphere is rigid, and the continental crust, all of them can be pushed down. Okay, that's why sometimes they break up and get into pieces and move around and so on and so forth. So as you begin to grow the ice sheet, the land surface gets depressed. So you have a total of 3 kilometer thick ice, but 1 kilometer of that glacier is actually below the surface level, and there is a delay in this as well. So ice load is added at, let's say, time 0. You're going from time of 1 to 20,000 years, and the immediate elastic response is kind of small, but over time the depression in the ice sheet under the ice sheet begins to grow. This is shown in kilometers, and you can see that the full bedrock depression doesn't appear till about 20,000 years. That can change the dynamics, because now, even though it's cold and ice is the glacier has built up to 3 kilometers, because it is depressed, the amount of cooling that happens when the air flows over it and so on will change, as opposed to here, right? If this is 3 kilometers, you will cool it much more, but here now you are only climbing 2 kilometers. So you have a feedback from the depression of the land to the processes that are going to affect accumulation, ablation, and so on and so forth. So just be aware of these difficulties and how they might affect the time scales that we see. So let's go back to look at some of the real data now. This is going back to about 3 million years from the present, and you can see that this is the deep ocean delta 018 sediment core from the North Atlantic Ocean, where you had glaciation on both North America and Europe and Greenland. So there are very strong signatures in terms of delta 018. Just remembering quickly, as you keep building glaciers, you are locking up more and more of the O16 in the glaciers. So the deep waters are getting more and more enriched in O18. So when O18 is high, the scale is reversed here. You have to be always aware, because in paleoclimate time always goes down and delta O18 typically is going the other way. Typically you have scales increasing this way, but here scale is increasing this way. So higher delta O18, temperatures are colder and there is more ice, whereas when delta O18 is less enriched, then you have warmer temperature and less ice. So you can see the time scale change happening here. Around 3 million years ago, when early human ancestors were beginning to evolve from gorillas and chimpanzees, when gorillas and chimpanzees mostly walk on all fours, when our ancestors began to work on 2 legs and so on, the glacial cycles had a prominent signature of 41,000 years, which you remember is the obliquity signature, insolation forcing by obliquity. And as you get closer to the last million years or so, there is some transition happening, and in the last million years there have been about 10 ice ages, and they have changed on the order of 100,000 years. So this is what the observations are saying. This is not something we are deciding. This is what the observations are saying, that the glaciations happened on obliquity time scales before. Somehow they switched to ellipticity cycles in the last million years. This is not completely explained. Okay, as I said before in the previous discussion we were having on this, that all sorts of complex dynamics of how glaciers melt, how they can slide to different latitudes because of the friction at the bottom with the ground and so on. All kinds of processes are invoked, including the fact that remember when I said that when the sun is here and the earth is going around here, it's moving faster. When it's on the other side, it's moving slower. So the summer is more intense when it's closer to here, but it's shorter, whereas when it's here, it's moving slower. It's farther, so summer is less intense, but summer is longer. So the integrated energy can be smaller here and higher here. Additional complication is that, remember, when you change obliquity, you are changing the radiation energy in opposite directions in the 2 hemispheres. So the summer is more intense in the hemisphere that is pointing towards the sun, but the winter is more intense on the other side. So the 2 hemispheric responses can be very different as well. So these combinations have to be always remembered. Again, you just want to be aware as a teacher, but you have to pick what are the main feedbacks you are going to teach the students that are then can be used for the global warming context. So ice sheet delta 018 changes in the last 150,000 years. So this is focusing more on the last ice age, and you can see that there are multiple time scales within it. So you have the precession time scale of 23,000 years. The overall ice age is on the ellipticity time scale of 100,000 years, but within that there are hiccups of obliquity forcing as well. which means the glacier is not just growing, but it's growing in spurts where you can see the growth and then some melting, growth and melting. This happened on 23,000 years cycle. There was growth again and then melting, and then growth on 41,000 year time scale. So clearly observations tell you something, but to interpret how the forcing worked, we need to develop the science, which is still being developed. You can look up many papers we will provide in the resources, but it's up to you how much details you want to get into for teaching. The more you learn, the easier it will be teach, in the sense that you don't have to teach everything you learned, but knowing the background material helps you explain things much better. That's something to remember. So ice cores are basically formed this way. The air is moving easily through when it's in the snow phase. As it gets compressed, snow falls in one season. If it doesn't melt in the summer, then more snow falls on top in the fall winter months. So the bubbles that get trapped, they can move through easily or diffuse when the ice is not very thick. But once glacier is heavily compressed and at its concentration, high concentrations, then the bubbles are essentially trapped. So when ice cores are taken, they have to basically determine the time scales that are preserved and the number of years that are preserved in the ice core. That's how these data are generated, and we will see that there is also carbon dioxide data in the same way. So when you combine some of the available tree rings, corals, ice cores, and instrumental records for the last couple of 100 years, this is how carbon dioxide looks. So we are now going back to carbon dioxide from glaciers and monsoon, because global warming always works through carbon dioxide. So glaciers change, carbon dioxide changes in addition to albedo and so on. Monsoons change, river runoff changes, upwelling changes, but still the radiative forcing eventually also goes back to how carbon cycle changes and how carbon dioxide changes. So you can see that carbon dioxide remained fairly constant at about 280 ppm till the Industrial Revolution began, and then it has been increasing super exponentially. And methane was at about 650 parts per billion. So this is parts per million by volume. This is parts per billion by volume. So you have to be always aware that methane is much smaller quantities, but it's 25 times more powerful as a greenhouse gas. So it's still very important. There are also differences in how long each one stays. Carbon dioxide is very inert, can stay for hundreds of years. Methane easily gets oxidized when exposed to oxygen in the air, so it only sticks around for about 8 to 10 years. So the differences in time scales are also important. So methane has also been increasing exponentially, basically comes from agriculture, water sitting behind dams, cattle, and so on and so forth. Why is this relevant? Basically we can go back and see how the carbon cycle has changed with orbital forcing, what kind of carbon dioxide signatures and methane signatures it has left. So to briefly recap what we learned about carbon reservoirs, delta C13, there is organic carbon on land, in vegetation, in the atmosphere, and in the ocean. The main thing to remember is again what we learned before: photosynthesis fractionates C13 and C12. Organic matter produced by photosynthesis tends to be depleted in C13 because C12 is preferentially taken because it's energetically more efficient to take up C12. So what is the signature left behind then? When C13 is different, that corresponds to a change in the concentration of carbon dioxide in the atmosphere. Why? When plenty of carbon dioxide is available, as much C12 as possible is taken up, so C13 is depleted by some, let's say, standard. If CO2 in the atmosphere decreases, then plants want CO2, so they will take up C13 as much as they need. So this delta C13 goes down, which means it becomes less negative, and if CO2 increases, then they will take up less C13. So, put it all together, then there are standard delta C13 values in the atmosphere, in vegetation, in grasses and so on, as we discussed before. Use these kind of data to go back and reconstruct. This is for the past about 1 million years from the ice core in Dome Sea in Antarctica. And you can see that there is a clear 100,000 year time scale in CO2, and that corresponds very well to the ice volume as we can measure from delta O18 in either benthic forams or deep water signatures and so on and so forth. So, the growth and decay of glacier volume directly corresponds to the growth and decrease of carbon dioxide in the atmosphere. Okay. So, what is the change? It's about 100 ppm. When glaciers are high in volume, so this is less volume here, more volume here. So, when volume is reduced, CO2 is at 280 ppm, that is our pre-industrial value. When glacier grows, CO2 is somehow taken out of the atmosphere, reduced by about 100 ppm. There are several theories as to why this happens. It's not completely understood exactly what determines how big the change is, but it basically involves vegetation being covered up or removed by the glaciers, ocean being covered by the glaciers, or when glacier volume is large, climate is very dry, it is more dusty, and when dust gets deposited on the ocean, it has iron. That iron can increase photosynthesis in the ocean, and increased photosynthesis can take down more carbon dioxide from the atmosphere. So, these are some multiple hypotheses. We don't know exactly which one worked or if they all worked together to produce this change. The main message for you is the CO2 in the atmosphere changes very coherently with the ice volume. Obviously, temperature does too, right? Why is this important? Because in global warming, we are doing exactly the opposite. We are increasing CO2 first, and then glaciers are responding. We are increasing CO2 first, and then temperatures are responding. So, both CO2 and temperature increase are going to affect the glaciers. So, we are in a reverse, doing things in a somewhat of a reverse way, because here orbital forcing initiates the retreat or advance of glaciers, and then vegetation, ocean circulation, dust content, etc. respond. That affects CO2, and then that CO2 in turn affects temperature and glacier growth. So, it is slightly different, but why do we look at it is because the feedbacks in the system should work exactly the same way. We will come back to this in a bit more detail when we do global warming, because it turns out that if you increase CO2 first, then how the temperature changes has very interesting lessons for us. Okay? Just remember those things. So, here are the glacial to interglacial changes in reservoirs. You are reducing carbon dioxide during the glacial times. So, you reduce it by about 25% on land, you reduce by about 30% in the surface ocean, but in the deep ocean you increase it by about 3%, in the atmosphere you reduce it by about 30%. So, this is kind of the complex story, and you can see that the delta O18 value corresponding to the ice volume and the delta C13 of the deep water are very much in phase. So, again basically confirms the idea that the carbon cycle that works with CO2 plus H2O giving you sugar or carbohydrate and producing oxygen is exporting that carbon down, where some of it gets respired back, but if it gets buried into the sediment, then that carbon molecule is CO2 molecule is taken out of the system. So, that is what we called the biological pump, right. This is the current distribution of biological production. This is grams carbon per centimeter squared per year, that is kind of the unit. You can now relate this to your circulation knowledge. We had Hadley cell coming down, high pressure, no upwelling, which means no nutrients. So, there is less production, less than 40 grams per centimeter square per year of carbon in the subtropical gyres. There are upwelling in the equatorial regions and coastal regions and some other regions here, where water is coming up, nutrients are coming up, light is available, photosynthesis is happening, and you are sequestering carbon, you are producing carbon. So, the production is high in the regions where there is upwelling, nutrient supply. The seasonality of production at high latitudes is a bit more complicated. We won't get into that in this course, but using those kind of relations between circulation, biological production, CO2 changes, and anaerobic respiration issues and production of methane, etc., you can see that in the last 150,000 years, very coherent signatures in both carbon dioxide and methane. So, this corresponds very well to the kind of time scales we saw in the 100,000 years in terms of 23,000 years, 41,000 years, and the overall 100,000 year time scale. So, this just reaffirms that the fact that human beings are perturbing carbon dioxide has to be very carefully monitored, because every evidence we have from the past says that carbon dioxide is a key player in climate change. That is at all time scales. Okay. So, what are the potential feedbacks? Some initial change happens due to orbital forcing. Let us say climate cools, that should increase snow and ice and increase albedo or reflectivity. So, there is more energy going to space, less energy being kept in the system. So, greater cooling happens. So, it will amplify the initial cooling. So, it is a positive feedback. Now, you can draw what happens when the initial change is a climate warming, and we should figure out why there are asymmetries, which we will come back to again and again. So, this is putting together the ice core data together in one plot. So, here is the carbon dioxide and the methane we looked at. Here is the temperature change we have looked at before, and you can see that they are all changing coherently. There are phase lags which we will not discuss right now, but once again I will point out that there is a slow change over 100,000 years, there is a fast change, there is a slow cooling, rapid warming, slow cooling, rapid warming, rapid increase in CO2, methane, temperature. So, this asymmetry is very important. We will come back to it, but it basically has to do with ice albedo feedback, but also what happens to snowfall and humidity when you are cooling versus when you are warming. So, we will discuss that later. And in the global warming context, as I said, we are increasing CO2 and methane first, and the temperature is responding, whereas here orbital forcing was giving you temperature change first, glacier was responding, and then CO2 and methane were responding. So, these asymmetries must be understood. So, the take home points from the orbital time scale climate change basically are that orbital parameters are three, they are very clearly defined. So, precession, obliquity changes, and ellipticity changes. But as we saw with a nice curve, there is ellipticity modulated precession cycle, and each one can combine with the other to produce multiple time scales. And as we saw here, there are internal feedbacks which can then produce additional time scales. We haven't gone into all the details because there are many unknown factors, unknown science. The science is still advancing as to why some of these time scales exist in the observed records. So, tectonic processes affect orbital parameters, as we saw with a figure. As continents move around, the Earth Moon system changes its orbital periods and length of day and gravitational pull and so on. That combines to affect the orbital parameters. The precession cycle and the obliquity cycle have changed over the evolution of the Earth, and ice sheets respond to orbital forcing and tectonic processes. It is very clear in all the geochemical evidences. So, as glacier builds, plates themselves move, and glacier melts, plates rebound. Those are the tectonic processes. Plus, when you move continents from higher latitudes to lower latitudes, glacier dynamics changes. And Just to re-emphasize, many timescales are observed in the geochemical records of past glacier volumes. Not all of them have been fully explained. It's a lot of science still to be done. And ice albedo feedback is one of the most important feedbacks. You should make sure you get a very good handle on it and teach it properly to the kids so that the kids know ice albedo feedback is very important and how it works. Global warming is worrisome because runaway glacier melts are possible. So you can see that we are not in the glacier building phase, which goes very slow. We are in the glacier melting phase, which can happen very rapidly. It's called abrupt climate change. We'll see examples of abrupt climate change when we come to the millennial timescale climate change, but we are in this phase. This is why we should understand very well the past feedbacks in the climate system. It's like having a rear view mirror in your car. You should always know what is coming from behind. In this case, we need to know what has been there before, so that as we go into the future and keep perturbing the climate, what big jumps are possible in the system, what abrupt changes are possible, what are the thresholds or switches and tipping points there are in the system, so that we don't kick it and create unintended consequences. So we'll see next time, switch to the glacial, deglacial timescales and look more carefully at some of these processes. See you next time.